and welcome to one and all for this online lecture. I am Dr. Supriya Bhalerao and I will be conducting today's lecture on inferential statistics. So what is inferential statistics all about? And it is nothing but to make the inferences. Make inferences about what? So there are two things about which we make inferences. First is hypothesis testing. That whenever you are doing any research, you basically test some hypothesis. You have some medical hypothesis which you want to test it either in a clinical study or in experimental setup. And the second thing is parameter estimation. I am sure you might have heard about confidence interval or point estimation, which we calculate from a small sample size which we take in our studies. So estimation of the parameters, there also we need inferential statistics. So basically what is inferential statistics? It depends upon the objective of your study. And what could be your objectives? One objective can be compare the observations made on two or more samples where you apply or where you can say that the data is parallel but is running in an independent group. So in two groups you are comparing two treatments A versus B, so that data becomes independent or unpaired. Or you want to compare in one sample only the effect of intervention, that is you take the readings before or after, or sometimes you take the readings over a time of series. For example, in case of diabetes or obesity, these kind of studies, if you are evaluating two drugs, then you may take the readings after a certain interval period, that day 30, day 60. So it will not be only before and after, so there will be a time series. There are studies like crossover where the kind of data which you collect, because the observations or the readings are taken on same sample or in one sample before and after or at different time points, it is called as a paired data, and you want to compare either the unpaired data or paired data. That can be objective of your study. And here what is important, that p-value, what is it, we will learn in this particular lecture. The another objective which you can have for your study is find out association between two different aspects of one population. So here the population is one, but you want to study like what is the association. For example, hours of sleep and age. So this kind of association, if you want to study that whether with increasing age hours of sleep go on decreasing. So this kind of association. Or you might want to study one aspect of two different populations. For example, what is the saliva output in young and old persons. So there are two different aspects of the population and you are studying one aspect. That means the parameter is only one. So this kind of objective also you can have for your study. And here the test which you apply or the statistics which you imply is association or relation testing. So if there is some association you find out, then you decide the nature of relation, and there the test of correlation comes in picture. There can be further different objectives, like given one set of values, can you predict other? So in this case, you come to know that height, if the height increases, weight increases. But after how much increase in height, how much weight increases? If you want to predict this kind of and if you want to do this kind of prediction analysis, then you have to use the test or the statistics which is called as regression analysis. And lastly, there can be a difference in occurrence of an event over a time period. For example, if you are giving some medication in pre-diabetic individuals, so how much time they take to convert into diabetics. So there can be two groups. One group is receiving some medicine and another group is not receiving any medicine, and you are following these pre-diabetic individuals over a period of time. And if you want to study that how many individuals convert into diabetes and after what time period, then the kind of analysis which you do is called as survival analysis. So these can be different objectives of your study, and based on these you conduct study and then you collect data and ultimately you apply statistical test. So why statistical test? Basically, where we need the statistical test. The first thing is to compare two or more groups or observations vis-a-vis differences and similarities between these groups or observations. Then to assign the probabilities to the differences seen. You want to study whether the probability of the difference which you have observed is high or low. And next thing is to prove the results achieved to meet the objectives are not by chance, because in medical field or in any other any field, whatever results you observe, you want to have confidence that the results are not by chance, they are the real results. Whatever you have observed, that is not because of any another factor which is influencing the results. So it should not be by chance, and that is what you find out using the statistical test, and ultimately to draw conclusions based on all these things. So what is the statistical means? On which basis you select a statistical test, or how the statistical test depend upon what? So the first thing is type of data collected in a study. So in this way, that I said that the earlier speaker has made my job easy. I don't have to go into the types of data. You have learned what are the different types of data. And then the next thing which we are going to learn is what is the distribution of the collected data. So far we were just labeling the data which we have collected, that whether it is categorical, nominal, ordinal, continuous, discrete. But now we will see what is the distribution of the collected data. And the selection of statistical test depends upon these two factors. You have also learned what are the levels of measurement. So basically continuous data has two levels of measurement, interval and ratio. And I am sure that this must have been also discussed in detail in the earlier lecture, that what is interval, what is ratio. One thing which I want to clear here, that never convert the data into lower level of the data types. For example, if you are collecting the data of weight, actual numbers if you have, never convert them in category like obese, overweight, underweight, because these are categories. And as you must have learned in the earlier lecture, that the nominal and ordinal, these data types are not, statistically that great as the interval, ratio, numerical values, because when you can measure something, you have to express them in numbers and not in categories. So never ever convert the data which you have collected in numbers into categories. This is a wrong practice and we shouldn't follow it in research. So we have discussed about the distribution of data. Now we will see, I am sure you must have heard this term normal distribution or Gaussian distribution. So we will see that what is the distribution of data. This normal or Gaussian distribution is also known as continuous probability distribution. So it is obvious that the distribution is applicable only to the continuous data. The German mathematician C.F. Gauss has invented this distribution curve, and that's why it is also called as Gaussian distribution. So what the normal distribution or the Gaussian distribution talks about? So it says that if we have mean in the middle, then the rest 50% data is scattered or spread on the both sides of mean equally. And this curve looks like a bell shaped, and this is a symmetrical curve, and that is known as normal distribution. So if the data falls 50% on either side of the mean, then that distribution is called as normal distribution. So as you can see the different characteristics of the normal distribution curve. For example, the highest point of the overlying normal curve is at the mean. As we move away from the mean in either direction, the height of curve decreases, approaching the zero, but you will see that this line will never reach to zero, or it will never touch the axis. It will always little above the axis. The curve will never, or the ends of the curve will never reach to zero. So these are few characteristics. Again, I have said this, that 50% of the data falls on each side of mean. So when you have continuous data, and in that data set, if the values fall 50% on either side of the mean, then you will call the data or the distribution of the data as normal distribution. So this is the different or further implication of the normal distribution curve. I am not sure whether you have undergone or you had the lecture of descriptive statistics, where there are concepts like measures of central tendency, which are mean, mode, median, or measures of variability like standard deviation, standard error of mean, range. If not, then you will have that lecture sometime in this 3 days course. But what the importance of this normal distribution and what is its relation with standard deviation and mean? We have seen that in earlier slide that mean is the peak point of the normal distribution curve, which is a bell-shaped in nature. And from this mean, if you go one standard deviation from either side, then it covers 68.3% of the data observations. When you move two standard deviations away from the mean, it covers almost 95.5% of the observations. If you move away three standard deviation, then it covers 99.7% of the observations. So as you move away from mean, more and more number of observations get covered under the area get covered under under this curve. Okay. Now coming to the data types, different aspect, like in the earlier lecture we have learned about the continuous, discrete, those kind of data types. But here for statistical test, the data is again divided into two different ways. So one data type is parametric data, where the distribution is normal. It follows the Gaussian curve. So that data is called as parametric data. And generally the interval data is parametric in nature. And then non-parametric data, where the underlying population distribution is not normal, and generally or by rule, the nominal and ordinal data are non-parametric in nature. So this you have to keep in mind while selecting the test. And these data types are based on the normal distribution, concept of normal distribution, which we have seen. So by default, you have to keep in mind that interval data is parametric in nature, whereas when it comes to nominal and ordinal data, they should be treated as non-parametric data. Now the question which will come in your mind, that how we should assess the normality. When we get a data series, how we should understand that whether this data is normally distributed or not normally distributed. So there I can tell you one rule of thumb. If the standard deviation of your data set is more than half of the mean, then the data is not normally distributed. Let us take one example and it will be very clear to you. Suppose mean of your observations is 4, and if the standard deviation is 3, that means half of the mean is 2, because mean is 4, so half of the mean is 2. And if your standard deviation is 3, that means it is more than 2, then in that case you will say that the data is not normally distributed. So this is a simple rule which you can keep in mind. But to test the normality, there are different tests available. I am not going to go into this test because for inferential statistics which we are going to deal, these tests are not that important. You use the softwares, and the softwares have inbuilt tests for normality, and they calculate the normality of the data themselves. So you don't have to worry, but you have to check whether the data is normal or not normal. It is generally seen when, or it is generally given when you export the data from Excel sheet to any software and you start applying the statistical test. The first thing which the software will give you is whether the data is not normally distributed or not normally distributed. But if you want to consider it manually, or if you want to just know whether it is not normally distributed or not normally distributed, the simple rule is half then mean. If the standard deviation is higher than half of the mean, then you will say that the data is not normally distributed. So suppose the data is not normally distributed, what you can do, because it is as we have seen in case of data types, that interval and ratio, they were shown like a ladder or the steps, and as you go higher, the quantity or the strength of data becomes stronger and stronger. So same way, when you apply parametric tests, then the robustness of those tests is more than the non-parametric test. So what you should do, if your data is not falling in the normal distribution curve, then there are simple techniques which you can follow and try to fit your data as a normally distributed data. The simple method which you can use, and that is more popular, that is log transformation of data. Or you can have other transformation methods such as squaring the data or taking square root of data. So different tests statisticians use to make the data, we can try whether the data can then fit into the normal distribution curve, and we can apply the parametric test. So this is the thing which you have to do before applying test. Now when it comes to statistical test, you must know that the resultant or the outcome, how we express the results of the test, or how we express the ultimate result of your whole exercise is based on theory of probability, which is also known as p-value. And you must have heard that this probability thing is based on the gambling. So the simple thing is, if you throw the dice for 6 times, what is the probability of getting 6? Then you know that it is 1 divided by 6. If you throw the dice for 6 times, the probability of getting 6 can be only 1, and then you will say that p is equal to 0.166. So if you actually throw a dice for 60 times, only likely that 6 will thrown 10 times. So this is the implication of whatever p-value we get, that if you do the things multiple times, then it will increase, the favorable event will increase in that multiple, in those multiples only. So this is the theory of probability, and we will check in terms of statistics also what it means. So probability of any event or outcome, if it is high, that if the thing is happening very frequently, it is not very rare, then you will say that probability is high. So probability of raining in July is very high, but probability of raining in October or November is low. So when the event is rare, the probability is low. When the event is not rare or not uncommon, we say that the probability is high. So in statistical terms, the event which is not rare is called as not significant, and the event which is rare is called as significant. We will see the examples and you will understand what I mean by this. But as of now, you have to remember that if the event is rare, then it is called as significant. If it is not rare, it is called as non-significant. So probability value is p-value, and value at which we regard an event as rare. So if you say that out of 90 days, if 10 days it rains, then you will call it as rare. Whatever level you consider, that is called as level of significance. So what is null hypothesis? Null hypothesis is basically an assumption while applying the statistical test, and we assume that there is no difference in the results of the two groups. So if you are comparing drug A versus drug B, suppose for antimicrobial activity, you will go with a null hypothesis that reduction in microbial count due to drug A is equal to drug B. So you go by the assumption that there is no difference. That is the basic assumption with which you go ahead, and then either you prove this or you reject this. So that is the whole crux of the inferential statistics. You start with the null hypothesis, and null hypothesis is always on the assumption that the two things which you are comparing are equal in nature. And there can be alternative hypothesis. So in this case, the alternative hypothesis can be A is not equal to B, A is better than B, A is far better than B, A is inferior to B, or A is very inferior to B. So these all can be alternative hypothesis which you can put across. But your null hypothesis will always be one, and that is both the drugs are equal. So now what you do? Reduction in cough due to drug A is equal to drug B. Is this a rare event or is this a not rare event? That you have to consider. So when you say that P is less than 0.05, or when you set the significance level as 0.05, what it means that there is less than 5% chance that drug A is equal to drug B will happen. So this situation that both the drugs are equal or they are showing equal results are less likely, very less likely. It is a rare event, and then you will call that the difference is statistically significant. So what I was telling you, that rare means significant and not rare is not significant, must be clear now, that what I mean to say. if the p-value is 0.0 less than 0.05, the chance of being these two drugs equal is less than 5%. That is the implication which we have to keep in mind, and in this case we will reject the null hypothesis. So if the probability is p less than 0.01, you will say that there is a 1 chance in 100, p less than 0.02, 1 chance in 50. It is very clear, it is simple mathematics. So statistical significance, which we have to keep in mind. I always tell when I take lectures on statistics that we are all medical doctors. We are not here to become statisticians, definitely not. And we do not like statistics also. And that's why we have left the subject of mathematics or statistics after 12th standard. We always wanted to do better in biological sciences, and that's why we have opted the careers in biology. And then when we have to learn these statistics again in our postgraduate days or in our PhD days, we find it very troublesome, confusing, and we feel that why we have to learn this again, which we have left 5 years back. So we have to simply understand that we definitely do not want to become statisticians. These statistics will not make us statisticians either, because whatever lectures we are taking or listening, learning are very basic in nature. So no one expects you to become statisticians, but simple things and simple facts should be clear enough in our mind. So whenever we do a research project and we go to the statisticians with our data, nobody should make fool of us. We should have, because the data is our own data, it is our efforts which we have planned the study, we have conducted the experiments, and the data when we take to the statistician, we should have at least an idea that which states to be applied and how we want to have the results, and whatever we are talking is not wrong. So these three things we have to confirm, we have to be very sure, and that's why we have to learn these statistics. So whenever we say that p less than 0.05, please understand that it deals with the rarity of the chances. It only talks about whether the event is rare or not, whether it is significant or not. It never tells you about the magnitude of values. What I mean to say that when you say that drug A and drug B, there is a statistical significant difference, the statistics doesn't tell you that whether A is better or B is better. It is just telling you that these two drugs are significantly different than each other. Then depending upon your objective, you will decide that this drug is showing better results or less results, and then you will say that this particular drug is significantly better than the other drug or not. For example, when you are working in a disease like obesity, you want the weight to be decreased after treatment. So the drug which will show the lower weights, you will say that it is better. But when you are working on hemoglobin levels, so if there is a difference between two groups, the drug which will show higher values, you will say that that drug is working better than the one which is showing lower values. So this is the importance that statistical tests do not tell you about magnitude of values. It just tells you whether the difference is because of chance or the real difference. This you have to keep or fix in your mind very precisely. Then the next concept which comes in case of hypothesis testing is type of error. And I'm sure you must have heard about these errors, type 1 error and type 2 error. The type 1 error is also known as alpha error or false positive error, where the null hypothesis stands, but test or the experiment which you do wrongly rejects hypothesis. So actually the null hypothesis is true, but the test wrongly rejects the hypothesis. That is a false positive, or the type 2 error, where test wrongly accepts hypothesis, which is called as false negative. But just remember that this type 1 error is labeled as or known as alpha error also. It is prefixed at 0.05, and what it means that 5% chance of accepting a drug which is not superior than conventional. So you are accepting only 5% chance that you will go wrong. So 95 times correctly the test or the experiment will correctly picks up that A and B are different. Then there is a type 2 error, which is also known as beta error, and it is prefixed at 20. So in 20 of 100 tests, new drug effects are considered same than conventional one, means you have a false negative, that is what it is called as, but in reality they are not. 20% of chance, it is fixed at 20, so 20% of chance of rejecting drug which is superior, and it is denoted by 1 beta, and 1 minus beta is known as power of the study. So when you say that beta error or type 2 error is 20, the power becomes 80%, and the relation between alpha and beta, power of the study is reciprocal. So when you say that alpha, when you reduces alpha from 0.05 to 0.01, the power of study increases. That is what the implication is. So these two errors we have to remember, and you will learn more in the lecture on sample size, as I said. So when you apply statistical tests, which are the basic steps? So first you have to select and use appropriate test, and that will be dependent on what is the objective. Remember the first slides which we have seen in this presentation, that what is the objective? It can be comparison, it can be association, it can be prediction. So different kinds of objectives will be there. Based on that your test will differ. What is the type of data? Whether it is nominal, ordinal, interval, ratio. So it will again influence your test selection. Then what is the distribution? We have seen normal, not normally distribution, and determine the p-value from the results. I mean, when you select a test, then you will apply the test, and then you will determine the p-value from the results. Compare it with the level which you have said or fixed as a level of significance, say 0.05 or 0.01. And if the p-value which you have got is less than the critical value, then the null hypothesis is rejected, and you will say that the drugs are statistically different, or there is a statistically significant difference between the two drugs. So that is what I said. Now how you will select a statistical test, and there is a checklist. First, which the all points we have discussed: objective of the study, then variable to be analyzed, say hemoglobin is a variable. Then you will decide what is a data type, whether it is numerical, ordinal, nominal, what kind of data type it is. Then what is the analysis type, whether you want to do comparison, association, regression. And then you will think that how many groups are there, 2 or more groups. So you are comparing A versus B, or you have A, B and C 3 drugs, and you are comparing 3 drugs with each other. Or in case of other type of studies, for example, if you are testing only one drug in obesity, but you have only pre and post readings, or you have readings at different time points, so accordingly the groups will be different, 2 or more. Then the next thing is distribution, whether it is normal distribution or not normally distribution. And for normal distribution and non-normal distribution, you will use in the software the question which will be asked to you is how many tails are there. So for normal distribution there will be 2 tails, because the data is falling on both the sides of mean equally, and it is running on both sides. So there are 2 tails of the data. For not normally distributed data, the data will be only on one side, and there will be only one tail. So these are the things which you have to plan, or which you have to understand before applying statistical test. So your test will dependent on these 6 variables: objective, variable, data type, analysis type, number of groups, and distribution. Now the tests are also based on the data is parametric or non-parametric. There are tests which are called as parametric or non-parametric tests. So the test which you apply for parametric data is called as obviously parametric test. So which data is parametric? We have seen that interval type of data is parametric. So whatever test we apply for interval data are called as parametric test. The tests which are applied to nominal or ordinal data are called as non-parametric test. So examples of parametric tests are t-test, ANOVA, Karl-Pearson correlation, and non-parametric tests are chi-square, Fisher's, Wilcoxon, so on. Now let us go into more detail. So suppose you have interval data. Obviously the test which you will apply are parametric test. If there is a single treatment and you are taking readings before and after, The test which you will apply is called as pair t-test. Two groups before and after the test is pair t-test. If there are multiple treatments or multiple time points, then you will apply repeated measures ANOVA. If there are two groups, that means you are comparing A versus B, then the test which you will apply is unpaired t-test. And if there are more than three groups, A, B and C, three treatments you are comparing, the test which you will apply is ANOVA. Association test we will have in a different table also, so maybe you can remember the first 4 points. If the data is nominal type and there is a single treatment before and after, you are comparing the nominal data, how many episodes of some illnesses were there before treatment and how many of them got reduced. So this kind of data is analyzed with a test called as McNemar's test. If there are multiple treatments, A versus B, you will have Cochrane's Q test. Then if there are two groups, chi-square, more than three groups also chi-square, and as I said, association we will see later on. So in case of ordinal data also you have different tests, and all these tests are summarized in this table, and this is enough for you to understand and how to read this table. So I will just tell you that first read the red things which are written. If the data is interval and unpaired, that means there are three groups and the data is interval, then you will apply which test. So that is if there are two groups, then T unpaired. If there are more than two groups, then it is ANOVA. So when there are more than two groups, the blue test will be applicable. When there are only two groups, the tests which are written in black color will be applicable. So the same thing which I have shown you in the slides before have been summarized in this table. And if you keep in mind only this table, it will be really helpful to you. For example, if there is a nominal data and the nominal and paired data, and there are two groups, you will apply McNemar's test. If nominal and paired data but more than two groups, you will apply Cochrane's Q test. So this is how you have to understand the table. Ordinal data unpaired, you will apply, if there are two groups, Wilcoxon-Ransom or Mann-Whitney test. If there are more than two groups, you will apply Kruskal-Wallis test. So everything which we have seen that in the slides before have been summarized here, and you can keep this table always in front of you whenever you want to select a test which is applicable, which is most preferable for your data. So as we have seen, what does the statistical test do? They analyze the data submitted by the researcher, calculate the chances of obtaining a difference. Remember that the statistical test does not indicate whether your design is right or wrong. Some people feel that statistical test, after applying statistical test, my design will become better. That is not the case. Whether the type of data is correct or wrong, that also statistical test will not tell you. You have to understand on your own that what kind of data you are dealing with. As we have already discussed, it doesn't tell you about the magnitude of the differences. And it also doesn't tell you whether the difference will be practically useful or not. So what is it? We will see in the last slide. So remember that statistical tests have limited implication. They just tell you whether the difference which you are seeing between the two treatments, whether it is because of chance, whether it is significant or not significant. It doesn't tell you anything else. So this is what all it can point out is whether the obtained difference between the two groups is real or it is false. So now we will take few examples and you will understand what I am discussing with you so far. So the first problem which we will solve is a group of 62 patients with iron deficiency anemia were treated with drug A for 3 months and the hemoglobin level was 12.2 gram per dl and the standard deviation is 0.5 gram per dl at the end of treatment. Another group of 45 patients treated with drug B, the hemoglobin was 12.8 gram per dl, SD 0.8. So now if you look at both the treatments and the hemoglobin values 12.2 and 12.8, it is really difficult for us to say that which drug is better. We cannot just predict based on these values that which hematinic you will prefer. So that's why we have to apply the statistical test. What they have given here, that assuming that both groups are normally distributed. So here the distribution has been already given to you. You need not to check the distribution again. Now, as I have told you, we have to go back to the checklist. So first is objective of the study. Here the objective is clear, that the drug A needs to be compared with drug B. What is the variable to be analyzed? It is hemoglobin. Which kind of data it is? It is a numerical data. What is the analysis type? It is comparison. Going further, how many groups are there? There are 2 treatments, so 2 groups. And the distribution, as it is already given in the problem, it is a normally distributed data. So this is how you have to apply actually this checklist to the kind of data or the information which is available with you, and then design whether it is a paired or unpaired. So you can say that it is 2 different groups. The data is collected on 2 different groups, not on the same subjects at different time points. So data is unpaired. So if this is clear for everyone, then we can see which test has to be applied here. It is a t-test, and that too unpaired t-test, because the groups are different. They are not pre and post in same group. So here the test is T, which is applicable only to 2 groups. Data is normally distributed, then only you can apply it. 2 samples have equal variance, that is something which is considered here. Unpaired and paired t-test depending upon the sample. If the observations are on same subjects, then it will be paired. If not, then it will be unpaired. And if the data is not normally distributed, then as we have seen, use non-parametric test, or you can try for the log transformation and then apply again the t-test. So what is a z-test? If the sample size is more than 100, then the t-test gets replaced by z-test. It is the same, function is same of both tests. It is just a factor of sample size. If sample size is more than 100, the test differs. If there would have been more than 2 groups, we would have applied ANOVA. So this is how you have to, understand which test to be applied. And once you have this kind of checklist ready for your data, whatever information is available with you, you can go back to the table which I have shown you, which was a summarized information about the statistical test, and then you can select the test which has to be applied. Now in case of ANOVA, you will find, or you will come across a term which is known as post hoc test, and there are different post hoc tests: 𝘠𝐾, 𝑑𝑛𝑒TS, 𝑉𝑜𝑛-Ferroni, Duns. You might have heard about these words or may not, but what is the function of this post hoc test? Remember that when you apply paired or unpaired t-test, there are only 2 groups. So the critical level or the significance level 0.05, which has been selected or which has been fixed, is applicable when there are 2 groups. When there are more than 2 groups, maybe the significance also need to be get distributed, and the significance level has to come down, maybe at 0.01 if you have 5 groups, or likewise how many groups you have, the level of significance may have to change. So these post hoc tests are applied to see whether the level of significance when there are different groups is again applicable, or whether there is any change. Now why these different tests are there, post hoc tests different? For example, this 𝘠𝐾 test, the 𝘠𝐾 test, all these tests have different assumptions and different comparator. 𝘠𝐾 test compare all the groups which are there in your whatever experiment with each other. So for example, if you have one control group and there are 4 different treatment groups, then 𝘠𝐾 test will be comparing all treatment groups with the control group. Or you can have test where every treatment, like 𝘚𝑛𝑒TS, multiple treatments compared with only one control group. So there will be no comparison between the treatment groups. If there are multiple treatment groups, they will not get compared, but every group will be get compared only with 𝘚𝑛𝑒TS. So these are the some variations in these 𝑉𝑜𝑛-Ferroni, 𝘠𝐾s, 𝘚𝑛𝑒TS, whatever post hoc test you are seeing. They are post hoc, called as post hoc, because first you have to apply the ANOVA test, Find out whether the p is less than 0.05. If the p is less than 0.05, then only you can go for post hoc test. If the p is greater than 0.05 in case of ANOVA, then you need not to apply all these tests. Let us take another example. From August to October 2011 in Mumbai, 911 patients were suffering from chronic diarrhea. 130 patients were given new ORS, oral rehydration solution, for 1 month. 31.5% of these 130 patients treated with new ORS did not have diarrheal episode in 1 month. Other 781 patients were instructed to take boiled water for 1 month. And 10.9% of the 781 patients also did not have any diarrheal episode in 1 month. So is there a difference between two treatments which are being compared here? The two treatments which are compared here are new ORS versus boiled water. So the objective of the study is comparison. Okay, then you have to go for the checklist again. Objective, comparison, variable to be analyzed is diarrheal episode, present or absent. So what is the data type here? It is nominal because presence of diarrheal episode or not present. This is the comparison which we have to make. Then analysis type is comparison because it is clearly written that what will be the comparison between the two groups. Number of groups, here again 2 groups because we are comparing ORS with boiled water. And distribution, we have to understand now whether this is a nominal data, so distribution concept is not applicable. Distribution is applicable only to the continuous data. That's why it is called as continuous probability distribution. Design paired or unpaired. So these are 2 different treatments, 2 different groups. So the data is unpaired. So we have now all the things with us. We have understood what is what. And then we have to go back to the table and select the test. You have to make such table now. New ORS, boiled water, no diarrheal episode or diarrheal episode. Now the values which we have seen here in this example are 31.5%, 10.9%. But you will get surprised that these values are not reflected in this table anywhere. The 130 and 781 patients are seen, but the values which we have seen in the example or in the problem are not seen here. So basically we have to understand the values which were shown in the example were expressed in percentages, but when you prepare a contingency table, you cannot have values in percentages. You have to make them in actual. You have to convert them in actual values. So when you say that 10.5% of 781 patients, it comes to 85 patients actually who have suffered from or who didn't have any diarrheal episode. So likewise you have to fill in this table. ORS taking individuals but no diarrheal episode, ORS taking but having diarrheal episodes, and similarly for boiled water, prepare this kind of table and then the test will be applied and you will get the result. Now as we have seen that the variation of t-test is z-test depending upon the sample size. In case of chi-square test, which is applicable on the previously shown example, there is something called as Fisher exact test. If the total sample size is less than 20, you have to use Fisher's exact test in place of chi-square test. Sometimes we have to apply Yates correction if any of the value, like here no value is less than 5. In any of the cell, the value is not less than 5. But if in your example of in your actual experiment, if any value is less than 5 or the sample size is less than 100, we have to apply this Yates correction. Now the things are so simple that we have softwares for everything. And mind you that the checklist which I have shown you, the statistical software exactly asks you the same questions. You have to just feed in the information, objective, comparison, whatever the variable is so and so, and whatever the checklist which we have seen, everything the statistical software keep you asking, and you have to just feed the information to the software, and then it will calculate the results and it will give you the p-value. So we need not to do much on the data, like whether I have to apply the Yates correction or not, that you don't have to keep it in mind. If any of your cell has the value less than 5, the software automatically applies the Yates correction. It is just for our understanding that such things happen and such things are there. So just to know, it is only for knowing the things. So whenever you prepare contingency table, there are various application. It is not only for Cochrane's test or chi-square test you prepare the contingency table, but contingency table you prepare for different things, risk ratio, relative risk, odds ratio. Even when you calculate specificity, sensitivity, there also you call 2x2 contingency table. What I meant to say, that 2x2 contingency table is not only applicable for the Fisher's exact test or chi-square test. It has a many different implications or applications as well. Moving further, the correlation and regression. So far we have seen the examples and the tests which are there in under the domain of comparison. Now we will see the correlation and regression. Again, based on your data types, different tests will be applied. Numerical data can be parametric, numerical data can be non-parametric, whereas categorical data will be treated only as one. And association or the correlation test which is applicable is contingency coefficient. If the numerical data is parametric in nature, then Pearson's correlation test is applied. So what is an example where you will apply the Pearson's correlation test? Suppose you want to find out, is there any correlation between number of ice cream cones sold and maximum temperature which has been reached in a particular day. So whether there is any correlation that as the temperature increases, the number of cones, ice cream cones sold are more. So both are in numbers, and there you can apply the Pearson's correlation test. If there is a non-parametric in case of numerical, if the data is non-parametric, then you will apply Spearman's correlation, and the example is whether the tip is given to pizza boy, yes or no, and at which floor he has delivered a pizza. So say for example, up to 3rd floor the tip is not given, but above 3rd floor the tip is given. So tip is expressed as yes or no, and number of floors is actually number. So when you want to study correlation between such two things, then Spearman's correlation is applied. And contingency coefficients is something where both the data are categorical, means where you want to apply the correlation, where you want to see the correlation. Both the data types are categorical in nature. For example, school performance of children and their socio-economic status. So both are categorical in nature. You have the grades for this. Then you will analyze the data with contingency coefficients. And you know that if the value is, Dr. Nilima has shown you that scatter plots have to be plotted for the correlation test, and if there is a positive correlation, you will find a line going upside, and if the coefficient is towards 1, you will say that there is a strong relation, strong positive relation. But if it is going towards 0.3, 0.2, you will say that the correlation is weak. And if it is on negative side, the coefficient which you get, that means one thing increases, the other thing decreases, that kind of negative correlation is there. Same thing, -1 indicates strong negative correlation, whereas -0.4, 0.3 indicates the weak correlation. So this is the concept of correlation. And the regression analysis is actually, once you know that there is some connection between two variables is there, but you want to see that after how much increase in temperature, the number of cones, ice cream cones which are sold increases by certain unit. So for 1 degree increase in temperatures, 5 more ice cream cones are sold. To find out such kind of precise predictability, you have to have regression analysis. And it is like, you might be remembering in school days we had a line equation. It is similar to that. You have equation something like this: y c is equal to ax plus b, And then in simple regression you have only one variable depending and one variable which is non-dependent and another variable which is dependent. So height and weight, average temperature in the day, and number of ice cream cones sold. So only one non-dependent and one dependent variable. But there can be multiple regression also when many factors decide the why. So for example, very close to our field is in a treatment we do not decide treatment based on only one criteria, but we see the age of patient, strength of patient, the clinical condition, and then we decide which drug has to be given. So treatment selection is based on many factors. So that can be multiple logistic, that can be equated with multiple logistic, whereas multiple logistic regression, whereas simple regression is only one factor deciding the other factor. Then like correlation for prediction of variable also, depending upon data, which test you will apply differs. And this is a simple kind of joke that in US it is said that when you see the more storks, then there is chances that the babies will come. So anyone who draws the causal conclusion that storks bring babies and shoots storks in the hopes of reducing the population will be wrong. So you have to ultimately, the whole thing about statistics is whatever you get, whatever p-value you get, you have to ultimately understand it in context of your problem, in context of your situation. Just because there is a positive correlation between number of stocks and the population increase, you cannot just shoot the stocks and the population will go down. This will be very wrong stretching or wrong assumption about this particular statistics. The next thing is association between exposure and outcomes. The simple example is smoking leading to lung cancer, and in this case also you will have a contingency table which we have seen in case of diarrheal episodes, but here the values which will be entered are different, and even the rows and columns are also different. Here how the contingency table is prepared, the column says that exposure is present and outcome is present. So lung cancer, I mean exposure is smoking, so smoking is there and lung cancer is there. How many individuals are like this? They will be put in a cell which is shown as A. Then exposure is absent, so there is no smoking, but still lung cancer is present. Will be the number which we will have will be put in the columns or in the cell C. Exposure is present, outcome is absent is B. Exposure absent and outcome also absent is D. And then based on this whole table you have different kind of statistics. You might have heard these words like risk ratio, then odds ratio, and how what is the implication of all these. But basically we have to understand that there is something called exposure, there is a outcome, and a classical example is smoking leading to lung cancer. You have these cells where you will enter the values of individuals which actually show these attributes and then calculate, and these are the simple mathematical calculations. There are no statistical tests here, just you have to calculate or divide different things. For odds ratio, A divided by C divided by B divided by D, and it is actually just remember that if odds ratio is 1, then the exposure does not affect odds of outcome. If odds ratio you get more than 1, then exposure is associated with higher odds of outcome. That means the smoking is associated with higher odds of lung cancer cases. If odds ratio is less than 1, exposure is associated with lower odds of outcome. And the last thing in the objective slide which we have seen was survival analysis, which is a time trend analysis. And basically it was suggested for cancer patients that when you give two different types of therapies over the time period, which treatment shows more number of days and which treatment shows more number of survival cases. But now this survival analysis is used for other events also. For example, time for a leg fracture to heal, time taken to exercise to maximum tolerance, time taken for an adverse event to appear, time taken for pre-diabetes to get converted into diabetics. So these are the different applications of the survival analysis, but basically it was first cancer test, and at the end you get this kind of curves, this kind of plots. So in you can see here that the blue is treatment group and group 2 is placebo, and you can see that in a placebo the survival probability has gone down very soon. All the cases or all the patients who were included died in a very short span, whereas in treatment group the patients survived, and you can more patients survived for the longer duration. So this is how you can compare the two treatment groups, and you can see there are some vertical lines which are seen on the graphs. So these are the actual cases when the patients died, or the way when the patient was censored from the study. So here the question is there a difference between time trends? And again you have two groups or more than two groups, and based on that you apply different survival test, mental Hensel test or log rank test or mental Cox test. So this is how the different tests are applicable, and you have to use different tests based on your objective. But do remember that whatever we apply, and somewhere I have said also that even if you get a statistical significance, it really doesn't mean clinical significance. So what is the meaning of this thing is, if you give hematinic, you may find that in every individual there is an increase of hemoglobin by 0.25, and a statistical test will show you highly statistical significant results. But is this 0.25 clinically meaningful? Of course, no. So what I mean to say that every time statistical significance is not equal to clinical significance. And why it is so? Because statistical significance is based on group of individuals, where clinical significance matters for single individual. In statistical significance, there is adequate amount of data, but when you talk about clinical significance, this kind of huge data is not available. Statistical significance is a probabilistic because it is based on the theory of probability, but clinical significance is related with the committed decisions, what exactly you are going to give to your patient. So generally I give an example that if a MR comes to you and says there are two MRs and both are selling some hematinic, and one MR says that the hematinic which I have increases the hemoglobin level in every patient by 0.5, and another MR says that in some patients it increases by 4, in some patients may remain constant, and in some patients it may show some decreasing trends also. So as a physician, which hematinic you will prefer? The one which is showing 0.5 results, or one which is showing good results in some patients and in some patients which is not showing results? So basically if you are a clinician, you may like to take a chance that the hematinic which is increasing in some patients in some patients by 4 gram per dl, you might prefer that. But as a researcher, it will be always the one which is showing consistent results. So statistical significance is based on measurements, whereas clinical significance is based on intuitions. So this is a difference, and that's why statistical significance does not essentially mean clinical significance. And we have to really judge whenever we are saying that this statistical significance is going to matter in my clinical practice. Lastly, who will do all these statistical tests and how you will perform? So there are different statistical softwares are available. I have listed a few for you. In my research, in my research I use GraphPad, and this is not a advertisement of GraphPad, but I find it very easy even as compared to SPSS, so I just use GraphPad. But you can use any software which you find convenient and comfortable with, and you can do the test on your own, or you can give them to statistician also. But whenever you give the data to statistician for analysis, never forget to have the checklist with you. in your mind or on paper ready for your data, so that whenever a statistician will ask you some questions, you will be well prepared and you will not go wrong in the selection of statistical test. So thank you very much.